welcome everybody. We're just really elated that everybody's here and everything is. We're going to focus this month quickly on rigging gear inspection. This is a very, very broad topic. It's sort of what are you going to put in, what are you going to take out type thing. But on your screen there, you'll see a variety of subject points that, in brief, we'll be addressing those. Just to let you know, there is, for reference points here, I'd like to at least put it into your library, into your thinking, that we have under the OSHA world, we have 29 CFR Code of Federal Regulations 1926.251, and that's rigging gear for construction. And then, of course, 29 CFR 1910.184, that is slings and rigging for general industry. And then under ASME B30.9 is the slings document, and the .26 document is for rigging hardware. So it'd be shackles, master links, hooks, shackles, master links, turnbuckles, eyebolts, hoist rings, and so on. And of course, the .10 is for hooks. So there's, make sure you got your library built. These certainly are free, the first two, and then the last few there are available at asme.org or through the ITI bookstore. But you want to make sure you have the latest versions up. I would suggest there is a 2014 just recently released document for the sling standard, and it's substantially taken on a new look. There are no more rated capacity tables. Those will be the rated capacity. The rigging, of course, is determined or deemed by the fabricator or manufacturer. So it's different, and we've dialed down quick into a variety of areas that have to do with how to arrive at rated capacity and so on. So it's a good document, and if you don't have it, I would highly recommend that you get it into your library. So the only one we're really kind of leaving out of here in the big discussion are metal mesh slings. And if you'd like to have more information about those, I would suggest you tackle that ASME B30.9. And they're about 1/4% of the market and used in some manufacturing, rarely used in lots of other areas. So if you deal with metal mesh slings, they won't be a part of our program today, but those are available for instruction and guidance on care, use, and inspection under that .9 document. In general, this is how we're going to tackle this. In general, the steel slings or metal slings versus the synthetic sling. So we have three chapters or three sling types. We have wire rope slings, we have alloy steel chain slings, and we have metal mesh slings that fall into that steel category. And in all cases, we have to have proper marking identification. In some cases, we call them tags. In some cases, they're stamped onto the device, like a metal mesh sling would be stamped onto the handle at one end or the other. So proper identification, because that identification carries with it the rated capacity, which is all important to us, and then it has other data. If it's a multi-leg bridle, it will have the capacity based on an angle, and so that's established for us, let's say at 60 degrees for a four-way. And so it gives us a rated capacity, and we'll call this 20,000 pounds at 60 degrees for that four-way. So we'll know what the rating is for the sling. There is some discussion. Eventually, I'd love to see us be able to put the angle capacity for multi-leg bridle and also the single vertical leg. I kind of like to have your input. If you'd like to email me at mike@iti.com, I'm going to propose to the B30.9 committee that we discuss putting on the single leg rating in addition to the multiple leg rating, because sometimes we'll grab a 4-way, use it for 2 legs, and we may have an offset center of gravity load. So knowing what the original single leg rating is, in addition to the combination of legs, might be very helpful. So any input that you have, I'd appreciate that. I know it's conversation may come back, well, gee, you have 2 rated capacities on the same sling. Well, it's really helpful to know what the original fabricator intended for single leg capacity, so that we can then make a calculation in the field for an offset CG type load, or 2 legs, 2 short legs one end, 2 long legs the other end if it's a chain sling, and so on. So input, feedback would be great. I'd appreciate it. The all steel slings, have that removal criteria that discusses metal loss and nicks and gouges. Metal loss really from abrasion, nicks and gouges, particularly wire rope slings, but it could be on hardware or chain links where they propagate. They'll end up propagating a fracture or crack, and so we may have a link that has a significant gouge for maybe a grinder. So certainly we're looking for and expecting one there's a minimum chain link dimension that we have to attend to, but number 2, even small nicks sometimes can be the initiation point for cracks. So whether it's on a link, chain link, a master link, a coupler link, anything that we want to create that V-notch, all of a sudden we can have a crack starting, and it's not very identifiable except for a real good hand-over-hand inspection. Also steel chain slings, wire rope slings, and metal mesh slings obviously are subject to corrosion. This is one of those things that when you take a look at a wire, and I know this sounds silly, but so we have the core and say a 6-strand type rope, and so the individual wires right out here that make up that outer layer, if those are heavily corroded or pitted, here's the idea. And if we take that one wire and just step it right out here, we can end up with corrosion that attacks the outside surface, and we have bare steel on the inside here, but we may have lost, let's just say we've lost 10% of the outside of that individual wire. And the deal is with wires, of course, they're round, and so corrosion can attack them circumferentially. But 10% of the outside skin of that wire, 2 things happen. Of course, we take away a lot of metal, a lot of cross-section, but also the cracks. If there's corrosion, there are small cracks that propagate down in the bottom of the corrosion pits, and can be really devastating from a loss of strength standpoint. So I'm going to take away this red circle here. And so the original, you can see the original versus the actual affected there. So 10% loss around the outside, when you really do the math, pi r squared, you find the area of that circle, and let's just say, in round numbers, we'll give it, whether it's millimeters or not, but we'll end up with 2 for that overall, and then 1.6 for that internal. And so when you do the math, you end up with losing 36% of the cross-section, and remaining is only 64%, even if there's no cracks propagated down the bottom of the pits. That's a huge loss, and I think it's probably the most deceiving inspection point we have is corrosion. It's the hardest one to really quantify, and we need to be most respectful of the results of corrosion and pitting. So that kind of loss is really a big deal, and we want to be really cautious about that. So let's take let's go on to then the balance of our little list there. And heat damage, of course, any kind of heat damage on hardware of any type, steel slings, chain, metal mesh, wire rope, or fittings, master links, and so on, I think what we want to appreciate is it's either cold drawn type material often, so that we take wire, and the wire is literally drawn in dies, in cold drawn dies, and reduced in diameter. And I'm just doing a little freehand here. So we take that. So there are dies put in locations here as the wire is drawn down. An alloy chain is really the same way. So the grain pattern back here in the steel starts out like snowballs, and then as it goes through the drawing die, then the grains get longer, and that's what really gains the strength in a wire, or a forging, or a link, or drawn in a chain links. So we gain the strength. The strength is really increased because of this elongation of the grain pattern right there. And when we heat it, when we heat that wire with a spark, or we torch it or cut it or get it hot, what happens, and I'll just sort of magnify this. So here's our grain pattern right now inside that wire. It's nice and long, and it gives it its ductility and strength. And then what happens is it recreates that snowball right there and changes that back from a long grain pattern to short, where the spark or where the heat is activated there, and all of a sudden we can get a crack or a breakup to start right there. So heat and steel, drawn wires, forged products, and things like that really don't do well when they're affected by high heat. And you want to be very cautious. We had a question come in the other day about lightning strikes on cranes, and our advisement is, if you know a crane has been hit by lightning, our advisement is replace the ropes. I know that sounds harsh and mean and ugly, and you know, the idea is, well, go look for the damage, but these burn spots on the rope, as the heat electricity transfers down through the crane, can be very small and very difficult to find. But if you take that concept back, where we're really changing the grain pattern, we can have a very weak point in the rope and very difficult to find. Them only might be a couple of inches long or an inch long, where it's arced over to another steel component in the crane. So I would suggest to you that, boy, you know, if we've got a lightning strike on a crane, I would suggest it's really about risk and lowering the risk, and I would suggest to you that we just eliminate that risk and get new rope on the crane. And that can be a very expensive adventure for sure. I'm not discounting that, but really something to take in consideration. Let's drop down here right to synthetic slings, and we have some items here, of course, again, messing illegible tags, holes, tears, cuts, punctures, crushing, really pitting and corrosion of the metal in fittings if there are any, broken or cracked, distorted in fittings, and then UV damage really on those that have the muscle exposed to the sun or to welding. And that's pretty much limited to a web sling or a synthetic rope sling, not particularly current testing, not to round slings at this time, since they have a jacketed cover, and the cover is not load-bearing, all the muscle is inside. So UV really is predominant potential to web and rope. Let's go on to so those were general inspection points. On wire rope slings particularly, we have the good old rule of thumb here, 10 broken wires in a rope lay, randomly distributed, or 5 in a strand in a lay. And so a rope lay, if we consider this to be 6-strand rope, I'm going to count 1, 2, 3, 4, 5, 6, 1, 2, 3, and so on. So I'm going to start that laid measurement there at the beginning of 1 and beginning of 1. So anywhere in that range, typically, as you all know, most sling ropes, wire ropes used for slings, get torn, shredded, ripped because of corner contact on square edges and other abrasive surfaces. So it's not going to be fatigue as a general rule. It's not going to be anything related to vibration. It's going to generally be an external abuse and shredded wires. So really we're talking about losing a substantial part of the rope strength, and that's why we get pretty excited when we start seeing that. In addition, so two things, we have loss of strength, and that's always a driving decision by the inspector, whether it's frequent or periodic. Loss of strength, and in this case, we have a hazard as well, particularly with wire rope slings with hand punctures and so on. There's certain in industries that simply one broken wire is sufficient. They don't want to catch it in the glove and then be taken up out of the hold of the ship. So a lot of longshoremen and maritime industries have a much more restrictive broken wire criteria, only because it's a personal hazard, not as much as a strength issue. So depending on where you're at, what you're doing, be cognizant of that. Then we have other broken wire criteria here for braided slings, 2-part to 7 parts and 8 and 9 parts, and then an overall reduction of diameter of the sling body of 5% or more. And that sort of replaced our 1/3 of outer wear of the outer wire, and our criteria used to be 1/3 of the outer wire diameter. Very hard to evaluate, very hard to measure. So we just really went to a 5% overall reduction of the rope's catalog diameter. So if it's 1-inch catalog, then it would be 0.95 would be the removal point. And typically what happens there is we'll get some, we may get some internal damage or nicking and gouging inside, but generally we're going to get abrasion to the outside of the sling, and metal loss will help create that loss of diameter. And we've lost enough cross-section that we want to go ahead and kick that sling out of service. And anytime we remove slings or rigging from service, we want to make them non-functional, non-operational. And I would suggest your organization have some disposal plan for making the slings so they're not usable anymore. Cut the eyes out of them, save the tags, and send them back to the tool room, and they can get reordered and so on. But have a disposal plan. Before we go to this first picture, I did want to show you something really important. I got an email yesterday from an organization. I've blacked out their name and so on, so don't be offended, but something that was sent to them. You can see in the upper right-hand picture is an unswedged sleeve. You can see there's no flashing marks on it. It's fairly large in diameter and short. Compared to down below there is a swedged sleeve that's actually been pressed, much longer, smaller diameter, and so on. So the organization received slings in that had not been pressed, swedged at the eyes for the mechanical splice finish, and at the initial inspection. So I think the key is to remember we actually have 3 inspections that we want folks to adhere to, and that one is initial, and then frequent, and then periodic, and/or which is annual. But in that initial inspection, that's really where you're going to catch. These are new slings or new pieces of rigging just received, and that's where we're going to have hopefully caught something like this, that as the tool room received this, starting to hang slings up, they're looking at the slings before they put them into service, and gee, the rigging shop forgot to swedge it, forgot to press it. So bad way to start a day. Good way to have a sling failure, an accident, and load on the ground faster than you figured on. So it's something to look at. We want to be trained in what to look for and making sure we can identify whether a rigging component has been properly fabricated. So just a word to the wise. On this screenshot here, we have a damaged sling. And those in the room, you may have 2 or 3 looking at the screen together, or 20 or 1, but take a look. This is a wire rope sling, and see if you can identify cause of failure or cause of rejection or removal from service. Give you a second there. We don't have answer keys to go with this, so you can see. We're going to, we have 2 good reasons to remove this sling from service. One is metal loss. If you'll note right above, right up above those wires that are torn there, and right below, you'll see a substantial painting and flattening and metal loss. And also, obviously, we have broken wires right here in that, and that would meet our criteria for 10 broken wires in a lay or 5 in 1 strand in a lay. Let's take a look at another one. There you go. So this is really, there's a difference in ropeology that has to do with dog legs. A dog leg is really a fold or a collapsing, a pushing of the strands, outer strands into the core. And so it's like a cardboard fold that completely creates an imbalance, that we have an out of balance condition of all strands trying to do their job, and they're not equally loaded. And so when we straighten that sling back out, and I'll just do kind of a, here's the eye swedge sleeve, and we get this and that, and all of a sudden right here we've got that dog leg, and we may have a 60% sling or 50% sling in that case, and it certainly would take our sling out of service. One thing I want you to please be respective of is when we talk about damage and removal criteria, if you really kind of do, if you do the wire count, let's say 10 broken wires in a lay length, out of, you would rarely have a wire rope sling that has 100 wires in it. Normally, even a 6x26, 6×3, 156, so 10 broken wires out of 156 wires in the outer strands. Geez, we're like at 7.5% or so. So we're really not giving up much when we say we need to kick a sling out of service. So if we think we've got 5 to 7 or 8% loss of strength just from broken wires, and we get all hyped up about that, which we should, well, when we get an out of balance condition like a dog leg like this, and when we lose 30 to 50% of the balance of the strands, that's a huge number. So we want to be really responsive to the damage that, because that sling under load, under tension, what's going to happen is the strands that are making the shortest pass on the inside are now in a super tension, and the ones that are on the outside are humped, and they're on vacation. You know, there's no load to them when it's been really deformed in that type of position. So just an idea. You know, it's one thing to look at the OSHA requirements and the ASME and say, well, okay, dog legs, yes, I understand. But, you know, to take it to a technical and a physics standpoint, there's real reasons that we want to get really quickly reactive to some of these. And when we have 5 or 8% of loss by broken wires versus 30 to 50% by a strong dog leg, huge difference. And the rest of it might look peachy keen and just nice and fine, but it's a substantial loss of muscle there. So that's a reason to take it out of service. So let's take a look then also what is sometimes called the dog leg, but is in this case, this is actually a kink. A kink is a turn in a wire rope, whether it's wire rope or running rope or a sling. It's a complete rotation, a 180 rotation, and then you pull through under tension. So you might be rigging up a load, and you got we've thrown the loop in the sling leg, and we didn't catch it, and we pull up with the crane, and we throw this, you know, the old Missouri phrase was the old throw a cat's ass into the rope body, and it's literally taken that loop and tightening it up. And we've now created this either open turn or closed turn, one way or the other, depending on the rope lay. And talk about out of balance, you know, we have 70 to 80% of the rope body out of balance there. Everything's completely distorted. We have severe rope structure distortion, and it's certainly a candidate. It's certainly out of business at that moment in time. Okay. All right. So let's. So those are physical properties in addition to corrosion, metal loss, tagging identification, infittings, and all those other things. These are specific areas that we thought we'd cover this morning. And of course, then this one, you should have seen the other end of the sling. It actually, this was and I will say, one thing you really want to watch out for is long-term installations. This is really a good life lesson here noted by this incident. It did drop a lubricating system onto a drill floor and injured a person. So the sling was really up and over. It was up and over in an inverted basket hitch, over a hook and regularly place them. It was there all the time, shackled to a lubricator down below. So it's every day, all day. It's hanging up there, supporting this lubricator. Well, we have severe wear and metal loss at the eyes, right down here where they're bearing into that shackle and hinging in the wind, you might say. Notice, if you can, I'm going to bounce this screen up just for a second. Let me go up to 200% here and see if I can get this into view. You can see the shredded wires right there on the end where it was contacting the shackle. Nobody pulled it down. Nobody looked at it. It was there forever, and nobody had really disassembled it to look at it. So it was hanging components regularly up in the air. And then look at the sleeve right here. Look at the damage where the sleeve-to-sleeve contact. One sleeve was literally adjacent to its brother's sleeve and rubbing against it, and causing that severe metal loss there. And any sleeve damage is rejectable criteria. There's certainly broken wires right down below. You can see those based on the blow up here. There's broken wires. They're all chafing and ripped and shredded wires there. The sleeve is damaged, and obviously we have lots of broken wires up there. And as I said, to start this out with, you should have seen the other end because it was completely parted, and that's what caused the load to fall. So not a good day. Long-term installation can get us in the worst way, and we want to be really cautious about inspecting our rigging every day. And even if it's assigned to hold something up overhead and be pulled down under a counterweight system or something, we want to be looking at that installation and that application, that it's as well as we just hand rig that for the first time in the morning. We need to inspect it. So when things are pulled up out of the way and you can get to them, you really want to do a healthy inspection. Okay. All right. Very good. Let's take a look at chain for just a minute. And remember, our initial list talked about metal loss, corrosion, deformation, and so on. Chain and chain slings, they're some of my favorite tools. We use a lot of them. We use a lot of adjustable chain slings to rig a lot of loads, and they're very robust. This is an easy one. We just took one sling leg and laid it against another chain sling leg, and notice just counting the lengths. Just if you look at that tape measure right there and count that length as number 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We'll call it 15 links right there. Okay, so we have 15 links on the top leg section, which these are in the same assembly, and we only have 14 links on the bottom, if you count all those out, actually. So we have substantial elongation. It's not interlink wear. You can actually see that the barrel, the pitch is changed. Notice that the height of that link versus the height of the link down below, substantially different. Let me take those marks away so you can get a better view of that. And the elongation, you know, one thing that if you really want to identify chain link measurements, one thing you can do is to actually measure the outside end to outside end of the link. So let's just say that that's 2.44 inches, and the brother links downstream, outside end, using large calipers and just measuring the outside end of the link. Downstream, there may be measuring 2.62. Well, definitely we have elongation. That's no concept of interlink wear. Whatever the links do when they contact each other inside, interlink wear is one issue, yes, but overall elongation could be measured outside to outside and then compared to other links in the assembly, and then you can get a double check and you know you've got elongation happening. We want to make sure that we have links that are free to hinge and adjacent to one another. If they're locked up, they're probably collapsing and getting long, and or we have interlink wear, and or to a coupler. And we certainly see some damage in some of the links down here by collapsing and elongation. So just things to you know, sometimes I'll take a chain sling when I'm on in a facility, take a sling, and even though it's just a frequent inspection, I may take that sling and lay it down here, and I'll bring back, and the hook will be right here. And so I'm going to compare these lengths adjacent to one another over a given distance. And again, if I can get down to where I'm looking at, gee, I've got 14 on this side from weld to weld, and then I've got 15 on this side. You know, here's my healthy side, you might say. This may be the elongated side, and or interlink wear. So I'm going to be hard looking at those lengths, both for twisting, collapsing, elongation, and so on. So you can just do it on a shop floor. Just lay it down, put the lower end up against the upper end, and just get a leg-by-leg comparison, a section-by-section comparison. Easy to do. So let's see what we got here. Then let's go to the next frame. Thanks, everybody, for sticking with me. We're just having some fun this morning. These, all these slings, all the pictures that you see in any of these presentations right here are pulled from service. This is a chain with a grab hook on the end. A couple things with it. We have spreading. So we have tip loaded. And if we go by the ASME document, we're going to say not needs to be spread. It needs to be less than or equal to 5%, not to exceed 1/4 inch. And the other part of that is 0 degrees twist, or it's unbent from the plane of the hook, is kind of how the wording goes. So we definitely have that. We have significant wear or metal loss down in the bowl of that hook. Though it's a grab hook, you can pretty well see that we've got some metal loss right there. And we have substandard connectors. Take a look at this top link right here. We can buy those at Walmart or Kmart, and they're just a boat chain anchor connector. It's called a quick link, and it's non-alloy. Somebody just decided I'm going to slap a grab hook on the end of my chain, cut off whatever was there, if there was anything, and put on a quick link and a grab hook and made a sling out of it. Well, not a great idea. So we have field alterations to the sling, and we got a huge problem on our hands, and so we would reject this completely and get it out of service, or whatever other damage might be there. We've already got this guy identified, and we're going to say, no, we're done, and get rid of this, and really try to find out, how did this come to be? Can we stop this homemade chain sling activity, because we really need to have quality gear for folks that are working near the load. Next page here, this is kind of a good, let me balance this one up for us as well, just so you can see there. Notice this was a chain sling I took out of service. I said, wow, look at this. So the link itself, notice that the top portion of that link has a huge step in it. It's really a misweld right there, so it's really a homemade master link. We wouldn't find that from CM or Crosby or Gunnebo or anybody like that. So you can really, and there's no markings on the master link itself, but it's a really poor job of joining the link ends together. So that starts to kick off suspicions. One other thing of real note, so we'll say homemade link. It's going to be my first suspicion, and just sort of call it like it is, let somebody else prove you different, because that's not would be coming out of the national and international manufacturers that we really know of. The second item down here is really a substandard hook. It is the grade, I'll just say on sling assemblies, grade 80, grade 100, grade 120, and those approved grades for overhead rigging and lifting that have been pre-proof tested. They're going to have keeper pins in the connections and basically no cotter keys. So you can tell right off the bat, well, geez, look at this cotter key right here, and I know I've got a problem already that cotter key is non-standard to alloy fittings. and it is likely a grade 7 or grade 4. Somebody just put on a grab hook to try to make a shortening system for a chain sling after receipt. So it's kind of homemade applied, it's shop applied, and not healthy for us. We may have a sling assembly here that's 8,800 pounds with all pre-proof tested components, and all of a sudden we get to this guy down here, and his working load limit may be at 3,200 pounds at 3-to-1. So we have substantially, when you take that, you're under 10,000, you're less than 10,000 braking strength, it's not proof tested, substandard components, and on alloy up here, you know, we're in the 32 to 34,000 pound range for braking strength. Substantially different, weaker all the way around, non-acceptable. So let's not be adding anything or letting anybody add to our chain slings once they get fabricated. We have proper ways to do that. We can send them back to the fabricator. Their name is on the tag. Let them do the upgrades as necessary. I still got the picture magnified. We'll do that for this one here. Bring this into view. Chain sling here, this is a 2-leg assembly. Notice that it does have those basically headless pins, and there are roll pins that keep the pin in place on the other side. It's a little out of view there. So it is the right unit, but notice the blistering. It's particularly right here on this hook, and the difference in coloration. Notice the color right up here versus the color all the way down through the rest of the chain, and definitely the coloration down through the hooks. And those hooks have actually been superheated, and we actually have puddling right up here on the tip of that hook where it's starting to move material around. So paint's blistered, everything. So we have really a condition here where we have heat damage is the culprit. Coloration change, bluing or browning of the steel, puddling, and so remember our discussion about quick heating and quick cooling. Well, this would be typical of that. These hooks may have been working around the furnace area and they just got super exposed, and now we have breakdown of material. So we're out of service for that assembly, and don't think we can really salvage much in the chain, certainly, or the fittings, the hooks. I don't know that we really want to be salvaging the master link or couplers at the upper end. We might as well just toss this whole thing and make it non-functional, and let's get it off the floor and get it out of service. Let's go back to our web sling subject then. And we have synthetic web slings besides what we talked about early on. We have broken and worn stitching in the load-bearing splices, chemical damage, meat melting or charring, which is heat damage, or knots in any part of the body of the sling. Initially we had UV damage, cuts, punctures, tears, and then fittings damage. So those are a combined type condition or rejection points. Notice this one, and then let me bounce these pictures up for us just a little bit. This is an end fitting. It's a triangle choker. There's a smaller triangle on the other end that passes right through the middle right there for choking. But notice that we have substantial deformation. Right up here we probably have, so we have a bend. You know, if we run a straight line up through the fitting right there, sorry about that, just run a straight line, and then we have this bend or sweep in that component right there. We have a deformed in fitting, and so it's out of service. What happens is, you know, if we try to take that from a side view, try to take that fitting, and it was in this position, and that's its original shape, and, you know, it likes load in through the axis, right through the middle of that fitting. That's a good thing. But if we bend it, when we try to put load to it, now it tries to straighten out. And we have this steel trying to change position every time it takes load. So, you know, it's an easy thing to propagate a crack right there in the middle where once it's bent, now we're trying to straighten it back out, and eventually we can have a crack and have a catastrophic failure, because all hardware that's bent like that wants to return and respond to the load in its axis. and we can certainly have unexpected failure at the worst possible time. So bent, damaged material like that, quickly out of service. In this case, I would do a quick look at UV ray degradation of the sling body down here. It's really amplified by bleaching and loss of coloration. Also a cotton feel to the sling surface, where the fibers really, what happens is pretty cool that you get down to taking a look at the fiber itself, and the fibers really should be nice and smooth all the way down. This is just sort of a side view of that material. And so when we run our fingers down along there, it should be slick, almost lubricated, and very low coefficient of friction. But when we get heat and damage starts to accrue, UV degradation, all those little fibers start to break up, and they start to stand up like the little tiny hairs on the top of my head. And for anybody that knows me, I'm getting balder with age here. So, but these little hairs stand up there, and they have a cottony feel to them. They feel like a little, stands of cotton, and they're rough to the touch. And those fibers start to stand up, so it feels like cotton, which is a little rougher, rough surface versus the smooth, slick surface. You get a little microscope on there, and you'll be shocked at how the fibers are literally burned by the sunlight or welding, and they just stand up. And it's all breakup of those fibers that are exposed to that. So that, in addition to a bleaching or loss of coloration, very substantial evidence of UV. And the last item that I often look at is if this is a 2-ply sling, so we have a center ply right here, I'll often peel that open. And let me see if I can get this to go here. We'll do this. I'll peel that open, or try to open that up with my fingers, and see if I can see a brilliant coloration. And sometimes I'll see that brilliant color yellow in between 2 layers and 2 plies. And it's very white or cardboard colored, tan colored on the outside. But peeling those 2 plies apart, or down at the throat of the sling, where we'll have the sling is created into maybe a tapered eye. And so I'll search right down inside the throat right here and pull that sling open and see that brilliant coloration inside, and it's very white outside. And it's very, very quickly you can identify that is UV, and that's going to be our main problem. So just things to think about. How can I tell that? Is that an issue, and so on. All right, very good. Let's take a look at the next one. I'll bring this into view. We've brought in some pictures for you today, and I just want to help highlight some areas that could be key concern. What are our thoughts there? Anybody tossing that out? I don't have a live reader board here on my screen, so I'm just working away, but this is acid damage. It's actually battery acid. So we have a chemical damage sling. We're going to, we're going to have disturbed and melted fibers often. You want to be wearing gloves when you're doing this. You can put your sniffer to work and see if you can smell anything odd coming from the slings. It often will be brittle, and the sling is almost burned in place. So you'll have have a caking or having a melting or fusing of the fibers together. But chemical damage is very common and just something to be aware of. So going to get that odd look, and it can even happen to a brand new sling. So be really cautious of that. If you think it's paint, do an inspection, do a deeper inspection, and make sure you know what you're looking at. Paint's not all that great for a sling. There's no really super harsh chemicals that can affect it, but determine that paint versus acid would be the question. So let's take a look then at another photo here of a sling body. This is fairly small, but we have 2 things going on. Can everybody see that? Hope your screen's blown up there. So we have some abrasion. We have standing fibers. We have some cuts going across here, and we also have some melting. Other than that, it's a perfectly good sling. So notice where the sling is fused right here, right in that area, and it's actually plasticized, and we would want to certainly kick it out for that sling. The web slings almost have a zero defect removal criteria, so just about anything we do to a web sling is going to cause question. We also kind of have a question UV, the discoloration that's in that area versus what's further up on their screen, so UV question. The cuts right down here, we have opening that ply up there and cuts up above, and some potential abrasion adjacent to that. So like I said, other than that, it's probably a really good sling, but this one will need to take out of service. It's certainly more than met any removal criteria in any one of the three categories by themselves, and it just happens to be all of them combined. This happens a lot when slings slide along a surface and move across edges, and this certainly is. I can't be a bigger proponent that sling protection would be our best friend here, and that is something with synthetic products and sometimes wire rope and sometimes chain, but sling protection is a huge investment we want to make in our organizations to help prevent this. I mean, you got to look at this sling and say, geez, for the sling to slide to 3 or 4 inches and to acquire that kind of damage, we were not very far away from actually burning right through the sling or cutting all the way through it quickly. So we were just, it's a miracle that we were able to set the load down and not have a total sling failure. So sling protection's our best friend. And then round slings, let's take a look then at this guy and get a bigger picture. It's kind of interesting to see these slings actually being manufactured. Round slings have an inner core yarn series, sometimes parallel, sometimes in newer designs they're going to a spiral strand, but the yarns are taken around a drive wheel and then passed around a tail roll and then through the cover. And they're taken multiple turns, sometimes 20, 30, 60, 100, 150 turns, and then they snip off the end of the yarn, and sometimes they'll tape. They'll do packaging tape across the body to just sort of join it different places. That's not rejectable. That's just manufacturing. Sometimes you'll feel small knots created by the manufacturer to just join the 2 loose ends of that core yarn in a single sling. Not a big deal. Knots in the body, knots in the overall body is a big deal, but the internal knots created by tying the 2 small yarns together is typical, so not rejectable. That once that those turns are taken, the slings will be taken off that mass coiling system, and then the cover right here, that red orange looking cover, will be spread over the sling in both directions. Right now it's all bunched up, but it'll be spread over there and then sewn down, and then tagged and ready for service. So so from a rejection standpoint, broken or damaged core yarns, the core yarns are the muscle. That's the white stuff right here. So if we can see exposed core yarns, that's rejected. If you can see through the cover and see penetration and see the core yarns, that's a rejection point. Also, if we can feel along and we have rebounded or backlash core yarns, that would be another rejection point. Knots in the overall sling body would certainly be restriction or constriction of the core yarns, and then heat damage, weld splatter, anything else that's penetrating the sling would take it out of service as well. So let's see, we've got a round sling here. This guy is about a 15,000-pound capacity sling. I'd say, like anything else, when you can read the newspaper through your sling, it's probably rejectable. So in this case, we've got a huge puncture. You know, maybe that's our formal term for it. The real reason, according to B30.9, is cut cover, and exposed core yarns, and that would be a reason for rejection. So notice there is a double wall for that sling. There's a red inner cover and a yellow outer cover. But at the end of the day, if we can see the core yarns, which we can, then the sling is rejectable. Sling here, we've got a nice round sling that's had a rough day. So it's missing or illegible identification. So we're missing all that information. We need to know what the capacity of the rigging is before we start hanging it on the hook and trying to use it. And we got to have it. We got to have the rate capacity. And of course, then this one, this is a really fun sling here. This guy, there were two of these on a concrete slab being picked up, and the sling simply ran across the surface of the concrete. It was pretty fresh, no sling protection. And this is, they dropped the slab, broke the concrete slab, broke the trailer on which it was just coming off, and stood the semi up off the ground in the front end. So other than that, they had a nice day. But this guy, this particular sling is like a, if I recall, it's at least a 30,000-pound capacity sling. It's a huge sling. But you can see the metal, the melting right in here. You can see that abrasion damage. There's fusion and melting of the outside cover. We can certainly see the core yarns right through there, but what you're not seeing is the other part of this sling that was totally sheared as it slid across the concrete edge and is total failed, pretty much cut like you would with some shears. So this was just an area that did survive, and the other 10 feet away, we had a total failure. So good example of cutting damage to a round sling, unfortunately, and no injuries. That was a good accident to have if you have to have one. They didn't have to take anybody to the hospital. So, and then let's see this guy right here, and it's probably pretty evident. We have all kinds of, everybody's with me? We got all kinds of heat damage. So we've got heat damage. We've got weld, slag, and splatter all over the sling body. You can see the fusing right there of the outside cover. You have to assume that the inside core yarns have also been somewhat melted, fused together, compromised, so that all those yarns that are inside the sling that are running inside the jacket parallel, have small fusion points all over them, and they were been superheated and they're all melted together. So that sling's toast, pardon the pun, but it's out of service as well. All right, excellent. Okay, so let's take a look then. Just a real short section here on synthetic rope slings. They're of course, like they can be braided or plaited or twisted strand. In this case, this is a nice little example from Samson. If you'd like to get, they've got a really good online, and actually I got an app on my phone from Samson. Let's just write this up here, SAMSON.com, and you can get an app for your phone that actually has this this chart on it, and it shows good material. And notice the green, the progression from green to red. So right here we're in green. That's good. That's okay. There's a little bit of roughing up of the outside external surfaces, and then we get down to the orange here, and we get into further issues, possibly yellow and orange, to some surface damage, and they finally get to the red section down here, where we're to the rejection stage, where we have fibers that are torn, shredded, melted, internal and external, and we've got serious loss of strength, and that's always the deal. So go into Samson's site. You can download their app onto your iPad or onto your phone, and or get their documentation off their website. So nice little visual to have as to the condition of rope, synthetic rope. And we're getting into some very high-strength slings. In this day and age, they're going to give round slings a run for their money for soft slings that can lift a lot of capacity. So they've got these slings capable in hundreds of tons of capacity. So here's a nice little sling. This is a braided, plated sling. It's a 2-in-1 double braid. This little guy, just the eye of that sling, if you take a hard look, let me bounce this magnification up here a little bit, and hopefully we can see this a little better. Notice we've got a very significant but kind of hiding cut right there. And we're actually literally seeing right through the sling rope structure. substantial distance there. We have an external cut, and I'll try to make a cut right here to there. We actually have that much, and I'll remove those marks so you can see we've got a severe cutting of about 4 strands and significant loss of strength right there. And that's easy to do. You know, again, sling protection's your best friend. So significant cut, and we would take that little guy out of service, reject it, cut the eyes out of it so nobody else can use it. Let's go to the next one. So that's a rejectable sling, round sling. Let's get this guy into view. I just want to make sure and blow these up so you can see them a little better on your computers. And what do you think the damage there is? Let's take a look. So you can see across the sling surface right here. Notice right in here, particularly right there, right up here, significant fusion, melting of the yarns, of the fibers on the outside. The braids are all literally plasticized. So we have real heat damage. And this can come and does come from putting synthetic rigging of any type onto hot objects. This particular one was rigged to a piece in a welding shop. They just wanted to pick it up and off the table and move it off. Well, they didn't let the steel cool down. We got right into the hot stuff, and you know we've got a real problem right here where now we plasticize it. We literally destroyed probably 30 to 40% of the cross section of that sling body, completely out of service immediately. So heat and synthetic materials don't go together. You know, the average, I think, average temperature range is somewhere about the plus 180 Fahrenheit range is about the top end. You'll get some other numbers that are about 194, 196. But if it's too hot to put your hand on it, it's probably too hot for a synthetic sling. So let it cool down or get another sling type to help handle that object. Now let's get this guy into shape here. And so there's a sling surface, and we're going to reject that one based on, if you go back and remember that Samson display of material disturbance there, we're going to call this one out because of moderate to heavy abrasion right there. So we're going to take that out of service. We've lost a lot of strength from the outside jacket, and we're going to reject that one based on, you know, when we go back to that Samson. Let me see if I can find that really quick. Right here, I'll bring this into view. You know, we're probably down here in that disturbance. I'd say we're easily down here into this, one of these two ranges right here where we've got some significant external damage, and you know, we've got an issue. It's a loss of strength. Always consider loss of strength in addition to the real easy ones. Reasons we take rigging out of service because of loss of strength. All right, so let's go. Let me get back to our screen size here, and hope everybody's having fun. We're just taking a look through the balance of these things. And now we're going to go off into hardware, rigging hardware, shackles, and so on. But the key here is fairly easy as a general subject. So we're looking at identification for most components. In most cases, we will need to have at least the manufacturer and at least a stock code number or a size of component. In some cases, we're going to need capacity. In some cases, we'll need the grade because it may be called out by spec information. So, meaning, let's just take shackles for a minute. So generally we'll need manufacturer, rate of capacity, and size as a general initial marking. Eyebolts are different, and eyebolts don't require a capacity. They come off a spec sheet. So then in that case for eyebolts, we're looking, or turnbuckles is another one. So they're really looking for the manufacturer and either stock number or we'll say size. So it could be 5/8, ½ inch, 1 inch, size or grade, stock number, and manufacturer. And we have to go look up that capacity. Often with our rigging at our facilities and on location, we will go ahead and ask the owner of that hardware to go ahead and tag or mark that with capacity, so we always have it in the hands of the rigging crew, so we always know what the capacity is for rated load, so we understand what our anticipated sling tension is going to do to it. So not all hardware will come with rated load on it. If you can imagine a master link, and this is very common, where we have a master link that's used for, it can be used as a free piece of rigging. There's a thing of beauty. There you go. All right, so we've got a master link here. We can use it as sort of a substitute shackle. We hang that off the hook, and we hang other shackles from that, and then we get and hang some slings from that. So master links can be independent rigging components. But when we buy them, when you and I buy them, we'll have the size, typically, and the manufacturer will be listed, and maybe a stock code or other pieces of information. But because a master link can be integrated with other rigging components, and let's just say it's used on a four-way, this is a wire rope bridle, and it might be used on a four-way chain bridle. So this is alloy chain sling, alloy steel chain. So you have two different kinds of slings that are built into using a master link. But the tag on this wire rope assembly, it may state at 16,800 pounds, and the tag on this chain sling assembly may be 18,000 pounds. In both cases, the master link is suitable for both of those applications, but the tag on the sling assembly will represent the sling assembly's rated capacity. So that's why they don't mark master links for capacity, because they can be integrated into rigging assemblies, sling assemblies. So when we buy our master links and use them as independent links, we actually attach a tag to that master link with rated capacity, working load limit, manufacturer, size, and so on. And we actually tag our master links so that we know what we can depend on them for rating when we're using them as independent devices. But when they're incorporated into a sling assembly, we'll respect or go by the assembly rating, and the master link just needs, the fabricator will just need to ensure that the master link in both cases has at least a minimum to be able to carry the intended load. Okay? All right, so we're always looking, as we said earlier, and this is really an easy laundry list for hardware. Almost all hardware is going to be inspected for deformation. That's bending or reshaping it from its original as manufactured condition. Heat damage, which can be coloration, bluing or browning of the steel, nicks and gouges, as we talked earlier, and then metal loss. No big shocks there. And for shackles, missing or legible identification. And then we have heat, corrosion, elongation, damage, bending, twisting, 10% reduction of diameter, nicks, gouges. I told my wife I wanted to name our first two sons Nick and Gouge, but she didn't really think too much of that, so that didn't happen. So, but it's a good thing for a guy in the rigging business. So, but then thread damage, of course, and then making sure that the pin is fully engaged, whether it's into a nut, bolt, and cotter key assembly or into a screw pin assembly like this. So let's take a look then. I've got some pictures of some damaged, these were shackles taken out of service. Oh my goodness, so we got one here that's really, I don't know that we have, I'm going to put up here markings, question mark. I'd have to look at the other side of the shackle, but the way it's pitted, we already have a big problem there. So pitting, and we have a substandard pin. And we can tell that's pretty well stainless steel pin in that shackle. Look at the holes not fitting right. I mean, everything's wrong with it. Just a bolt out of the bolt bend, and somebody slapped it in there for a connection. So, and look at the material loss up here at the top end. I'd have to really question. I mean, other than that, we have no other complaints with this shackle, but except for material loss, markings, pitting, a substandard pin. Otherwise, it's perfectly in healthy condition. So there's an immediate reject right there. Let's take a look. Let me get this guy into view. All right. And notice, here's what's happening. Is a little bit of a fold. You know, the shackles actually move a lot if you really do a lot of inspections. Look at this peak. You almost have a peak happening right there. So that instead of a nice arch, we have almost a fold happening up at the top of the bow. So that's not good. And we may have, you know, we may have a metal loss issue, question mark up here. I think we have deformation occurring right up there. And notice the span, and you know, comparing to other shackles, we can either do an interior measurement inside ear to ear, and because we're noticing it's not shouldering up and we have an excessive amount of threads beyond the outside on the far side, it's telling us really, I think in the big picture of life here, we have elongation. So it's going long. This shackle is going long this way, and we have a collapsing of the shackle ears. And they're very representative of overload. We're starting to take this, the ductility of the shackle is moving, and we have a collapse and elongation simultaneous. And I'd say we definitely have structural damage to the shackle. Fortunately, for whatever reason, we're able to get that pin in and out, but we have movement in the bow and in the overall body of the shackle total. So definite rejection criteria has been met, and a candidate is good. This would make a great teaching shackle. So if you want to have a little rigging class in-house, you know, find some of these kinds of components, bring them in, build yourselves a little rigging toolbox, all tagged and marked rejection, and teach from these. These are great examples to show others, because you can't always have a 30-year career in the first 6 months of your occupation. So it's really good to catch up the new folks with some of the damage types that they may see downstream. So let's take another one here. So that is rejectable, and here's a good one. All right, so take a look at this guy, and notice, you know, here's one thing I want you to really take a hard look at. If we put a straight edge on this shackle right here, see if I can do this drawing. Notice right there that, wow, we're out of alignment here, and we do a vertical and horizontal. Really, the shackle is racked. You know, if you take a look at the squareness or almost squareness of this ear versus the other one, and the out of planeness of the pin, you know, we're way out of 90 there, and the whole thing looks like it's racked. And this is often, you know, we don't have full pin seating here. This is something that happens quite often. We might have a corner of a load that looks like this, and an ear that's welded right there, and somebody has taken the shackle and rigged this shackle in here, and it goes out like that, and then we impose a lift like this. So we'll put a sling in here and pull up on it, and so we're side loading that shackle, and that's a very, you know, this is a kind of a way that happens. And so we all know that we're supposed to take 50% of the shackle's capacity when we do a single side load like that. We also have a great opportunity to rip that honkin' pad eye off of there, so hopefully it's reinforced. But we can bend that tab up, no problem. The other thing that we could do with that really, you know, is to go to plan B and not use the shackle in that condition, in that position, and really actually install a swivel hoist string right in here. So let me take that back just for a second. And a swivel hoist string probably is our best friend. We've got it here seated through bolted, torqued, and that the bail of the swivel hoist string works right there. Then we could shackle from there up and over, and then sling up from there. So we move our moment arm in considerably. Here's another piece of hardware that's doing the job that we're trying to make a shackle do, and actually we're helping the load out considerably. Our moment arm is much shorter from there to there versus way out to here, and so the bending and levering on that pad eye is much less reduced, and we're actually not putting any hardware into a hard bind, and letting the hoist string do a vertical lift and the shackle connected to the sling and so on. So really kind of a misapplication. That's really sometimes how these things happen. So check the squareness of your shackles. You'll be surprised how easily they get out of square because of different loading applications. All right, so we take a look at eye bolts here. Let's get down to, we're getting close here. Thanks everybody for hanging in there with me. Missing a legible identification. And we have kind of a laundry list like our other hardware components. Nicks, gouges, bending, crack components, twisting. We know we have a rated capacity adjustment based on the angle of loading in the plane of the eye from there out. And so that's what this table is about. Please respect that. I try to not use eye bolts anytime I can, and I try to use hoist strings, swivel hoist strings anytime I can to try to avoid this significant loss. I mean, look at that 30 degrees, the loss. We lose 75% at 30 degrees capacity there, 75% capacity. So, they just really don't. They're great boat anchors, but, for rigging tools, if I can avoid them, I will at all costs. So these aren't going to take long, but I just want you to see if we put a line through that guy and then through the upper section, that eye bolt has been twisted or bent sideways. So it's really bent out of plane. And something to be really aware of is any kind of angular loading is really, go back to that picture, is really in the plane of the eye. There's no rated load to pull off the side, broadside to an eye bolt. So it's just a big lever. And boy, they bend easy and snap fast. So something to be cognizant of. Yeah, this is ugly. So we have an eye, a weldable eye that's been welded onto a cap screw there. Notice that little piece of weld right in there. That's not good. So somebody's making up their own eye bolts, just happens to fit the right hole, and somebody wants to get creative. And it's just, boy, the welder in the wrong hands can create a lot of opportunity for damage and, if not, failures. So we've got a non-standard homemade eye bolt. Let's toss all those and make sure we get rid of those guys out of our inventory. And certainly then we have this one is, again, a bent component, and we got an issue right there. So really, once we start deforming them, immediately out of service. So. And this is a hoist string we put in. There is some moderate to medium oxidation, corrosion, maybe some pitting. But of most importance to us, if you look right down there at the bottom, is the damaged threads. And that would be an immediate reject. Don't know that we could really clean that up and knock that rust and corrosion off of there enough to salvage that hoist string. But we'd have to replace that. I'd send it back to the manufacturer, particularly, if it's a 1 inch or bigger. A lot of money we're talking about, and maybe they can do a cleanup and see if that's recoverable and salvageable. And then also we're replacing the bolt, checking the bushing, and doing a qualified replacement evaluation. Something I really want you to know about is these stirrup pins right here. Always double check stirrup pins on these hoist strings. The play and slop should be fairly limited or minimal, but sometimes if we put a big oversized pin right up here, it's just squeezing the living snot out of that bail with a shackle. Under load, it may want to spring away these legs as it forces up, and it can try to pop those stirrup pins out of there. So from an application standpoint, that pin that we put in there needs to be fairly reserved and not be where we're having to almost hand screw it into place. Likely is oversized for that bail. So be really careful and be looking for stirrup pin damage. Hooks, we talked about, we're just about done, 5%, not to exceed 1/4 inch. No side-to-side issues, and ability to lock, and that would be something like this, a locking style hook. We can replace a latch on a hook, but make sure that the hook is not spread and it's still in good condition, unauthorized welding or alterations. So just some things to think about. Well, there's an ugly ducking there. We got the plane of that eye versus the plane of the body. Really out of shape there. That looks like the hook was asked to go over the corner of the load and yard it over, so deformation immediately. We're way, anything past 0, we're in trouble. Spread hook here. That hook should be showing up and up here. So we've got hook spread, tip load, and we've got delamination right there down there in the bowl. And something really telling here is you look at enough swivel hooks, that swivel section right there, we're really normally in the 1/8 inch to 1/4 inch range, very small gap. Notice how big that gap is right there. And I could tell you right now, boy, we've got an overload, elongated shank, and tip loaded and delamination. That would be a good teaching piece. So just think about it. And then looks like a close examination here. We've got something non-uniform right there. And somebody has welded a company's initials on that to keep the slings and under the right ownership. Well, we already talked about heat damage as taking away the grain pattern and changing the molecular structure right in that zone. And so immediately that's a reject. Take it out of service. We can't afford to have that lifting loads around us. So Jonah, I'd like to see if we have any questions I can try to help answer right away, or you could certainly just drop me a quick email at mike@iti.com and let me know if I can help you with a 5-minute question here or there. Send me a picture if you want me to see something and help you take a look. And so I may have other questions for you to come back to. So Jonah, anything that we've got kind of burning fire here?
A lot of the questions were addressed by what you covered in the presentation. So I think, well, our audience is pretty knowledgeable, so I think they just got a little bit of ahead of points that you touched on. I'll shoot you one. We got this from Monty. He asked it when you were covering the Eyebolt. He was just wondering if Eyebolt and probably other hardware fall under the below the hook 1 or under the B30 standard.
Oh, that's a great question. Eyebolt, so all loose hardware, B30.26 is called rigging hardware. And in the scope of that rigging hardware standard is we give a scope definition of it. It's basically detachable hardware really intended between the slings and the load or sling to hook type combination. So it's we exclude. So a great question. So we exclude BTHs, below the hook lifting devices. They are their own device, custom designed lifting devices. So really we have BTH is really a custom lifting device, and the idea is that it's going to be covered under BTH-1 is ASME document for the engineering portion of it, for the design of, and then under the inspection side, it's going to be B30.20 is the user's guide for that for ASME. And under the rigging hardware standard that I mentioned a minute ago, B30.26, we have shackles, master links, which are the 3 standards are pair link, oblong master link, and round links. We have eye bolts, we have swivel hoist rings, we have eye nuts, and other equivalent connectors. They're called threaded connections or compression devices, turnbuckles, and then we have wedge sockets as a category, and we also have wire rope clips, which we only really like to use for anchoring things, not making slings out of. That's our preference. So all these other independent, and basically the way to think about it is these things are mass produced, where these are unique or one-off. And so so in B30.26 is where we'll find all these, and all their removal criteria and user's guide, operating and rigging practices all attend to those items. and they would not be in the BTH type standard. So it's a great question. Very different categories, and they have their own application. Okay, excellent question. Other questions?
Yeah, I know we're running out of time, but here's one last one from Trent concerning hooks. So he asked, when are hooks required to have a gate?
Well, let me share this with you. Really from the OSHA side and pretty much from the ASME side is hooks with latches are on hoisting equipment, and that means cranes, chain falls, chain hoists, come-alongs, things that are mechanical for hoisting or moving a load. There isn't, I have to go back to B30.10, but hooks are not always required on slings because slings are inert. And you think about a hook, a sling, here's a large wire rope sling with a foundry hook on it. So a foundry hook is an oversized bowl hook designed to pick up hot ladle components. And they don't have latches, and they're not supposed to have latches. They can't do their work if they got a latch. So a sling is not a machine in and of itself, and so typically they're preferred, but they're not required on slings. I don't know when they're not required on hoisting equipment. In almost all the standards and OSHA regulations, if it's a machine that's driven by gears, motors, brakes, all that stuff, all of those things have to have a latch to be able to retain the loose rigging that goes into the hook. The slings are not a machine. They're a connecting system, and they're not required to have latches unless they're required by the local jurisdiction. So that kind of is the defining line there, is the machinery have to have hook latches. The inert slings don't have to, but they are preferred. And if they're there, they need to be in good working condition. I hope that helps. Okay?
All right. Like I said before, a lot of the questions that you guys came up with, Mike touched on during the presentation. So I think we'll wrap it up with that for now. Thanks to Mike for putting his email on the screen there. If you guys do have future questions, I did want to remind everybody that, first of all, thank you for staying on the line longer than normal with us today. So the points and the information Mike was giving you guys, there's actually a 3-day course, and as I mentioned, it's going on at our training center right now. So getting 3 days worth of information down into an hour, that's why we named it a crash course, and I appreciate everybody's attention, and I hope you learned something today.
All right. Thanks, everybody, very much. We look forward to seeing you on a future webinar, and hope you have a great weekend coming up, and hope to see you soon. Take care, and we'll see you later.